Okay, so in Cosmology D3, which is the core part, the three main concepts which we will discuss are Hubble's law, then scale factor and how it is used to explain redshift. Earlier you would have heard of redshift as the Doppler effect. Okay, but now you will learn that Doppler effect is the wrong explanation for redshift. It's actually expansion of the universe. And the third one is cosmic microwave background radiation. And the fact that the universe is accelerating, the expansion of the universe is at an accelerating rate. So let's look at Hubble's law. Okay. So this graph you need to understand. Okay, so can you see the units here? It's in kilometer per second, and the x-axis is distance in megaparsecs. So what Hubble basically did is he looked at the data of around like 40 different galaxies which are very far away at different distances, and he measured their distance. So how he measured the distance is using the concept of type 1a supernova. Type 1a supernova means there is a white dwarf star which is part of a binary system, and it, due to gravitational pull, it eats up the neighboring star. So then the mass of the neighboring star starts entering the white dwarf star. Its mass increases beyond the Chandrasekhar limit, and so it becomes unstable, and then it explodes. So this is called a type 1a supernova. You also have a type 2 supernova, which is not of much use to us because its brightness will keep varying from star to star. Type 2 supernova is the red giant supernova. So you know, right, once the red giant expands, once the nuclear fusion is over, when the helium is also fused up fully, then the outer shell will expand too much and then it will blast. So that is type 2 supernova. So that it varies on the initial mass. Depending on the initial mass, the brightness will keep changing. So we can't make out by looking at the apparent brightness. When a star appears certain bright by some amount, we don't know whether it is so bright because it's too close or it's so bright because it's too luminous. So we can never know the true distance. But type 1a supernova, since it happens due to this process of eating a neighboring star and then exploding, somebody made a discovery that its luminosity during the supernova explosion varies like this. Sharply it varies. And this peak value is always same. Because this luminosity, energy radiated per second, it reaches a peak very quickly, and the span of time is 2 months. Over a span of 2 months, it reaches a peak. And this happens once in 1,000 years in a galaxy. I need a better marker. I have a marker, black marker. So once in 1,000 years it happens in a galaxy. So you can imagine how difficult it is to find this type 1a supernova. So they took some 40-50 years to identifying the universe, the visible universe, around 40 type 1a supernova, and you need to be able to see it before the peak has been reached in its explosion. So if you see a supernova suddenly appearing, so suppose this is a photograph of stars. Initially these are the stars present in that location. Suddenly you will see a new stars-like spot appearing, and then over a period of 1 or 2 weeks it will become brighter and brighter and brighter, and then it will again start becoming dimmer. So then you know it's a type 1a supernova. And the moment it reaches the peak, you will observe the apparent brightness. So apparent brightness, you remember, right? Apparent brightness is luminosity by the surface area.
Yeah.
If this is the star, the light from that star has reached the Earth. Earth's part is at a distance of d. So 4 pi d squared.
Yeah.
So this is known. This is known. So you can find out the distance of this star. And this star, this type of supernova is in some galaxy. Usually they will belong to one galaxy, another supernova will be in some other galaxy.
Yeah.
So if you know the distance of the star, you know the distance of that galaxy. Like that, he got the data of all the different galaxies, how far they are. Okay? So he plotted the distance of those galaxies on the x-axis.
Yeah.
On the y-axis, he plotted their velocities.
I already found the velocity.
Okay. So velocity, how he found is by the red shift. So from that supernova, light is coming to the Earth.
Yeah.
So if you look at the spectrum of that light, you will identify that the wavelengths, the typical spectral lines, whose wavelengths you know by the relative position, they are all shifted towards the red side. So if a line is supposed to be, say, 700 nanometer, it appears to be shifted to 710 nanometer, let us say. So this is called redshift. So you have learned earlier that it is due to Doppler effect. So he explained that the shift in wavelengths delta lambda by lambda is almost equal to V by C, where C is speed of light, V is the relative speed of that star with respect to us. Speed of recession. So for V much less than C, this relation holds. This delta lambda is actually the shift in wavelength. So that means, or let's call this lambda naught. Lambda naught is the source wavelength. Wavelength emitted at source. And this delta lambda is actually lambda minus lambda naught. This is the received wavelength.
Yeah.
So by the time it is received, the wavelength has become longer. So delta lambda gives you the increase in wavelength. So more the difference in velocity of the observed with respect to speed of light, more will be the observed shift. That means faster the galaxy which is moving away from us, more the shifting wavelength. Okay?
Yeah.
So we understood it as Doppler effect phenomenon. Right?
Yeah.
Just like sound, if the sound source is moving faster, you will hear a higher pitch. In lower pitch if it's going away, higher pitch if it's coming towards you. Right? Lower pitch means bigger wavelength.
Yeah.
Clear? But actual explanation is not Doppler effect. So actual explanation is the expansion of the universe. That means now you need to understand the Big Bang. We say that during the Big Bang, which happened around 13.8 billion years ago, the entire space which you see right now started from a single point. Okay? And time also started from that Big Bang only. So before the Big Bang there was no space, there was no time. So you can't ask what was there before time. It's a meaningless question. Okay? Now, when we see that galaxies are moving away from us, actually what is happening is you have to understand Big Bang using a balloon analogy. So if this is a balloon, imagine that you started off with a balloon of this much size, just bigger than an atom. And then the balloon is expanding till this much size. So when it was this big, suppose you marked 2 dots on it. Okay? When it was smaller, those dots come in closer.
Okay.
And when it is farther, the balloon has grown bigger, the dots have grown farther apart.
Yeah.
But actually the dot is not moving. The dot is at rest on the surface of the balloon. Only the balloon is getting bigger and bigger and bigger. And if somebody is standing on this dot and looking at someone else standing on this dot, he will think that he is moving away.
Yeah.
Agreed? The separation is increasing, so he will think he is at rest.
Yeah.
He will think, oh, he was earlier this much distance away, now he is this much distance away, he is moving away from me. That's what he will think. That's what we are observing.
Yeah.
Like this, if you go backwards in time, when it becomes a single point, so when the balloon started expanding, everywhere, every point on that surface is getting away from every other point. It's perfect symmetry.
Yeah.
You can't say any one point is the center and around it all the other points are moving away. The distance between any two points is increasing along the surface. Agreed? So when we say Big Bang happened, it happened at every single point at the same time. So every single point in our universe is the center of the universe. There is no one single center of the universe.
What? Why is that point central?
See, with respect to this guy, if you look at this point, he is going away.
Yeah.
If you look at this point, he is also going away. Agreed? So he will think that I am staying at rest. Since the beginning of the universe, I am staying at rest. Everything else expanded around me.
So relative to any point you take, things around it are expanding?
Yes.
Okay.
So every person will think he is the center of the universe. Everything else is going away from him. So by geometry, what do you think? If rays are diverging from you, you are the converging point. You are the focus. You are the center.
Yeah.
But this is true for every single observer. So that means there is no one single center of the universe. Every point is the center of the universe.
Sure.
It's very strange, right? Okay. So there is no one single center. Everybody is okay. So now the reason the person seems to be moving away is the expansion of the space, right? So distance is automatically increasing.
Yeah.
So now this redshift, how it is explained using this is by the concept of scale factor. So let us say the coordinates. So actually these two people are at the same location. They have not moved away, right? So let us say initially he was at x. So let us look at this curved path as a straight line, x-axis. Okay.
Yeah.
So person 1 was at coordinate x1, person 2 was at coordinate x2. So the difference or distance between them was delta x.
Yeah.
That is the difference in coordinates. Okay. Now, if the scale itself expands, the scale becomes like this, bigger, so that x1 is here and x2 is here. Even though the delta x is x2 minus x1, here also it is x2 minus x1.
Yeah. But it's bigger.
But the actual distance is bigger.
Yeah.
So it's like saying this is a meter scale and this is a kilometer scale. So the difference is, the actual distance is 1000 times bigger than this. Here it is 1 meter, here it is 1 kilometer.
Yeah.
So the actual distance is 1000 times greater. Right? So this multiplication factor of 1000 came into the picture here. That is called as the scale factor. So R is the scale factor. So since the universe is expanding, there is a scale factor associated with the universe. So the scale factor R is changing with time. Because the size of the universe is changing with time.
Yeah.
So right now the R has some value. Long back it was a much smaller value. In future it will be even bigger. So it's increasing with time. So this is the question, how does the scale factor of the universe change with time? What is the function of the scale factor as a function of time? Okay. So the actual distance. Okay, so now let us say initially, long back when the wave was emitted, the light wave was emitted. Suppose this was the wave. Distance between two crests is called as wavelength, right? So let us say this crest was at x1, this crest was at x2. So the difference in coordinates was delta x. But the actual wavelength, which you want to call it as lambda naught, will depend on the scale factor at that time. So let us say lambda naught was r naught delta x. And now the universe has expanded. So the scale factor has become new value. So that means this wavelength has become like this. It's become bigger in every way. Amplitude also seems to have become bigger. But now in electromagnetic waves, amplitude does not denote energy. In a classical mechanical wave, amplitude denotes energy. But in electromagnetic wave, it doesn't. So even though space stretches and amplitude apparently increases, it doesn't denote anything.
So is there any significance or no?
No, energy is carried by the frequency. Okay? And the frequency will decrease, so the energy content decreases. Okay. So delta x will remain same, but the wavelength we'll call it lambda. And this new wavelength will be the new scale factor times delta x. Agreed? So now if you look at the the redshift is denoted as z, which is delta lambda by lambda. Okay? And now if you, which is written as delta lambda by lambda naught, is written as lambda minus lambda naught by lambda naught, which is lambda by lambda naught minus 1. Agreed? But now if you see here, lambda by lambda naught is what? Lambda is r delta x. Agreed? And lambda naught is r naught delta x. So these two delta x will cancel out. You get lambda by lambda naught is r by r naught. Agreed? So you get your z as r by r naught minus 1, which is r minus r naught by r naught. So you get an explanation for redshift as happening due to a change in the scale factor of the universe and nothing to do with the actual motion of galaxies. This also helps you to explain one more paradox. You know that according to special theory of relativity, nothing can reach the speed of light. But we also know that the universe is accelerating. The expansion rate is accelerating. And Hubble made a discovery that more the distance of the galaxy from us, the faster it is going. So if you keep on increasing the distance, you will soon reach a stage where the speed reaches speed of light. And if you go even further, you will reach speed greater than light. So then, is a galaxy moving faster than light? It's not possible. Then how is it happening? So the answer is nothing is moving. The space is expanding. And space is empty space. Space can expand at any speed, it doesn't matter. Only stuff, real stuff cannot move. You getting it? So the expansion of space doesn't have any speed limit. So that's how this
paradox. You say expansion of the universe and expansion of space remain the same thing.
Universe is the space. So special theory of relativity is limit on speeds for objects, for particles which have mass, not empty space. Okay, so that's how this paradox is explained. So now, did you understand this graph? So Hubble found out the velocity using. Okay, now in this, how does V come into the picture? We know that Z is also equal to V by C, like that. So delta lambda by lambda naught we can find out from the spectrum. Lambda naught we know because every star has hydrogen. So if you see the hydrogen spectral lines, you know lambda naught, the corresponding line of that hydrogen spectrum, you know. And delta lambda, you know how much it has shifted from its expected position. So from this Z you know, but Z is B by C. Z is B by C. So these two you know means B you know. So you know this.
Yeah.
So by comparing B and D, you get a scatter plot which is to which you put a linear fit, and the slope of this will give you Hubble's constant. So the velocity is proportional to distance, and velocity is equal to h0 into d. H0 is called Hubble's constant.
Yeah.
Oh. Okay. So this is called Hubble's law also. V equals h0 d is called Hubble's law.
This is only for receding galaxies.
Yeah, all the galaxies,
Galaxies.
so everything you see are moving away from you because the space is expanding.
Didn't we learn earlier that what was it, two galaxies will collide in some years?
Okay, that brings another point. See, even though space is expanding and everything is moving away from everything else, okay, but then there will be some uneven distribution of mass and energy in the universe because you can't have perfect even distribution.
Yeah.
It's because there is some randomness, right? Even if you have a gas in a room, at certain moments you will find more atoms are accumulated in one region temporarily. So there will be some temporary density fluctuations. That is what leads to the formation of galaxies.
Okay.
So like that, if nearby galaxies are formed, even though the space is expanding, but when two nearby galaxies are formed, the gravitational pull will be stronger, and so they can go towards each other.
Right.
If they are nearby enough and if they are formed recently.
Yeah.
But if you consider far enough galaxies, the expansion of the space will dominate.
Yeah.
Okay? So these are local disturbances, colliding galaxies. But ultimately the universe is right now is proceeding towards the cold death. That means universe will expand, keep expanding, and the further you go in time, the acceleration will be more. So soon our own body will go apart. The atoms at the fingertips will go apart from the atoms in our body.
So become fatter.
You will stretch because everything is moving from its place.
Yeah.
So you will simply stretch out, and even inside your atoms, the electrons will stretch out of the atom like that. Everything will be split apart, and you will reach absolute zero Kelvin. That is cold death. Now already we are at 2.7 Kelvin. The average temperature of the universe is 2.7 Kelvin.
Oh.
So
Why does the temperature decrease if we expand?
why is the temperature decreasing? Good question. So see here, Wien's displacement law, do you recollect?
Very well. Oh, it's a high.
Black body radiation.
Temperature increases.
Yeah. So the product of the peak temperature and the product of the peak wavelength emitted in the spectrum and the temperature of the body which is emitting the radiation is a constant.
Okay, so by the shift that
So when you have Z is equal to delta lambda by lambda naught.
But these two lambdas are different, no? They're not the same lambda. No. It's not the same lambda.
Wait. So this is lambda by lambda naught minus 1, which is same as r by r naught minus 1. And we got lambda by lambda naught equals r by r naught. Agreed? Agreed?
Yeah.
Now, lambda naught is proportional to t. Lambda is proportional to, lambda t is a constant. So if we have lambda naught corresponding to a particular temperature, lambda will correspond to another temperature T. Okay?
Yeah.
The product of these two will be constant. So you will have lambda by lambda naught equals T naught by T.
Hmm.
Agreed?
Yeah.
So T will be
These aren't the same lambda knots, though, right?
what? Lambda naught refers to the
P.
wavelength, peak wavelength of the radiation when it was emitted.
Acha. Wasn't.
That happened long time back when the universe was smaller.
Yeah.
Lambda is the peak wavelength. That same peak wavelength when it is received, it is called lambda. Okay. So now the value, now this is still the peak wavelength only, but the value of the wavelength is different now.
Isn't the wavelength? You said the wavelength increases, right?
Yeah. That means temperature has to decrease, no?
Yeah. Okay.
That's why temperature decreases. Are you getting it?
Yeah.
If the peak wavelength which you have received is corresponding to a bigger wavelength, that means the temperature corresponding to that wavelength is smaller.
Smaller.
So that means the average temperature of the universe is smaller. So that's what we are getting to see here.
Yeah.
Corresponding to a bigger wavelength. So temperature equals T naught into R naught by R. And you know that R naught by R is less than 1. Because R is the scale factor which is going to be bigger than the original scale factor. Because with time its universe is expanding.
Sorry.
So the new temperature will be
Lower than
the original temperature. Clear?
Yeah.
So that's why temperature is decreasing. Okay, so Hubble's law is clear. So this is how you get D Cz by H naught. Is this clear?
Yeah.
Example, you can just try it out. It is simple only. Okay. Cosmic scale factor I have finished. Redshift also I have explained. Okay. Lambda by lambda naught is R by R naught. All these I have explained. This also I explained. Hot Big Bang creation of space-time also I explained. Okay, age of the universe. So we can estimate the age of the universe using Hubble's constant. See, the logic is like this. What pen is this? This is also not writing normally.
He is a blue moon. आपको अच्छी नहीं होनी चाहिए.
Okay. So this was velocity in kilometer per second and distance in megaparsec, right? And you got a straight line graph. So right now you look at a galaxy which is at a distance d, let us say. And from Hubble's law you get to know that its speed is d. Okay? So right now it is at a distance d.
Yeah.
That means when the universe was created, its distance from us was 0 because everything started from a single point. Agreed? So it has traveled a total distance of d. Okay?
Yeah.
So now if you assume that it has been traveling at the same speed right now, so we are going to get an overestimate. Overestimate of time of universe. Overestimate of the lifetime of universe. So actually we know that much greater rate in the beginning stage of the creation,
Let's slow down.
and then now it has slowed down. The rate at which
Yeah.
the universe is accelerating has slowed down. Okay, so that means initially it was expanding at a much greater rate.
Right, so
So if you take
the speed of expansion, you said is increasing, right? Or you said it might cross the speed of light.
yeah. Right
So-
now also the furthest ones are traveling. The space at the furthest reaches is expanding even greater speed.
So the acceleration is decreasing. Yes,
Yeah.
The velocity is increasing.
Velocity keeps increasing. The acceleration is decreasing. Earlier event is acceleration was increasing. Okay, that is called the inflation period. Okay. So now what we are saying is, suppose this galaxy right now is going at V. If we assume that it has been going at V only throughout, okay, then we know that distance is speed by time. So time is distance by speed.
Yeah.
So this distance is d and speed is
H0.
h naught d.
Yeah.
So d cancels and you get 1 by h naught as the time taken for the galaxy to reach this distance. So this is the estimate of the lifetime of the universe till now. So Hubble's constant is some 67 something kilometer per second
Yeah, 67 point.
per megaparsec. Okay? So 1 by 67 of that will give you the time in terms of 14.5 billion years, which is an overestimate.
Okay.
Because if you assume that it had a much greater speed for some some part of this lifetime, denominator would have been greater, your answer would have come out smaller. So we know from other sources, other data and all that, the actual lifetime is 13.8 billion years.
Wow, that's a huge one.
Okay? So this is the overestimate, thumb of rule estimation by now. Okay? So just check whether it's still recording.
Yeah, it is.
Okay. Okay. So then the cosmic microwave background radiation, this also I have explained actually. So that during the Big Bang, the temperature was like 10 power 34 Kelvin. So corresponding to that, the radiation was also very high, the radiation energy. But as the space expanded, the wavelength has also expanded. So frequency has decreased. So the energy has decreased, the energy density has decreased, temperature has also decreased. So this cosmic microwave background radiation was actually discovered by those scientists by accident. They erected these huge radio antennas and they were getting a continuous signal like a noise.
Yeah.
And they were wondering what is this noise? There is nothing, no source in this direction, still I am getting a signal.
Yeah.
So they try to clean it up, point it in different directions. Every direction it's coming. So it's in the microwave region. So it's in the microwave region because that corresponds to a black body which is radiating at 2.7 Kelvin temperature.
Yeah.
So since the universe is at this temperature, this universe is filled with this radiation. This was the radiation which was present when the universe was a single point, but its temperature was higher.
Okay.
So it's permeating the entire universe.
Now it's just like floating.
And the entire universe is now expanded to this much size, it's still there.
Sure.
The energy which was present when the universe was like a point is still present.
Yeah.
It has nowhere else to go. Where will it go? So this is the background radiation present everywhere. Okay? So that was detected. So this is called cosmic microwave background radiation.
Yeah.
Corresponds to 2.7 Kelvin. See 2.723 Kelvin. And it has some properties. It It is isotropic. Isotropic. That means directions doesn't change with direction. So any direction you point the antenna, you get the same kind of radiation coming from that direction. Yeah, symmetry with direction. So we have something called as a cosmological principle. So cosmological principle has two aspects. Which you need to know. Okay, can be asked as a 2-mark question. First one is principle of homogeneity. See, any model of the universe, cosmological model of the universe, which explains the creation of the universe, how it will evolve, how it will end, everything depends on, all those models have to follow these two principles. One is called principle of homogeneity, and the other is called isotropy. Okay? So isotropy means in any direction you go, you won't find any change happening, any difference. The universe is appearing the same in any direction. And homogeneity means, if right now if you look at the solar system, you can see that there is a star, then planets are orbiting at different distances from the star, and then you don't see any other solar system like this. So the universe seems to be different at different locations. But if you look at a bigger scale, large enough scale, say how big a scale? I'm not sure of the value, let us say 50 megaparsecs or something. If you take a cube of 50 megaparsecs and see from a distance, anywhere in the universe you take a 50 megaparsec side length cube, it appears to be the same. So it's uniform. So that is called homogeneous. You can't distinguish. So any model you come up with to describe the universe, it should satisfy these two principles. The universe doesn't have any special direction, and the universe is same everywhere in the volume. Now, principle of homogeneity leads to one conclusion, isotropy leads to one conclusion. What are those two conclusions? Can you guess? I'll tell you one conclusion. Universe doesn't have an edge. It can be due to which of these two principles?
So what was isotropy again?
Isotropy means in any direction you see, there should not be any change. For example, cosmic microwave background radiation. Any direction you aim your antenna, it's the exact same kind of radiation. You have microwave region which corresponds to a temperature of say 2.723 Kelvin. So this radiation is permeating everywhere in all directions. So universe doesn't have an edge. This can be a consequence of which of these two? Principle of homogeneity. Because see, if there is an edge of the universe, then something happening here is different from something happening here. Agreed? Then it means it's not homogeneous. Whatever is at the edge is different from whatever is at the center. So you can distinguish the volume at edge from volume at the center.
This cosmological principle, why did you introduce it? Like
any model of the universe, physics model of the universe which describes the evolution of the universe should satisfy the cosmological principle.
Okay.
So,
and this is one model.
Principle of
doesn't have an edge. That is one model. And
no, if at all the universe had an edge,
that can
it
be
will be violating the principle of homogeneity. So our universe cannot have an edge. Okay, and isotropy also, it leads to some conclusion. What could it be? Just look it up. Redshift is done. This is that supernova 1A. The peak luminosity is reaching, and this is plotted as a log graph because it goes many orders of magnitude variation. So to compress it in a graph, we have used log scale for vertical axis, and this is time in days. So you can see it goes till 60 days, 2 months. So this peak value of luminosity is same for all type 1a supernovae. That's why they are called as candles. Light candles. Standard candles. So you can see this picture also. Star without a supernova and then supernova suddenly appears there. See how bright it is. And then it will increase in brightness and then suddenly dim down. Okay, now we have finished D3 cosmology. We are going to further cosmology now.
Can we take a break, sir?
Need a break?
Half an hour.
Can we take a break after this? Okay, 5 minutes. Pause, stop the video there.